right, good afternoon everyone. My name's Tyler.
My name is NJ.
I'm Dale. My name's Scott.
My name's Matt.
And we're going to be presenting our suspension development for the Spartan Superway. So as an overview, I'm going to start off with a little intro as to why we're building a suspension system. Then NJ is going to go into a literature review. Dale, the functional specifications. Scott, deliverables. Matt, challenges. And lastly, Scott's going to go over responsibilities. So first off, I want some of you to just shout it out. What's missing from this picture? An engine.
Place to sit.
A seat. David got it. It's suspension. So for those of you who don't know, go-karts are one of the only transportation systems that do not have suspensions. And that's because the torsional flex of the chassis provides enough power, or enough flex to get power to the ground. So with Spartan Superway, we need a suspension because it's for rider comfort. So just like any bus or transportation system, rider comfort is one of the key points for the transportation system. In addition to that, there's also passive dampening. Passive dampening, such as you can see on top of the cabin over there. Coilover shocks, such as that. Reduce stress on parts. So if you have a system like we do now, the stress on hinges, joints, any pins is significantly increased without a spring or dampener on there. So now we're going to move into dynamic control of the cabin. So as some of you have seen, the city of San Jose, their buses are all kneeling buses, and with an active suspension such as this right here, which is linear actuators, it would provide the pods to move down into where people can easily get in and off, on and off. Lastly, pods must have the ability to traverse graded slopes. So this is where we bring in our active suspension, which is going to be 3 linear actuators, which we'll get into more later. And now I'm going to pass it off to NJ.
All right, so we all saw at the beginning of this class, in the beginning of the semester, we all saw all these automated transportations that's already been created and implemented. But the big problem that we have with these is, as we talked about, they're bulky. They're very bulky, big infrastructure to build them, to have them on. And they take more people than just a couple. They're more like a bus than a taxi fare. So we're not really interested in these. I'm not going to bore you with all these stuff you already know. What we're trying to do is the suspender way. And instead of having the track underneath, we're trying to have the truck above. It's going to be suspended. And there's a lot of these as well. That's the one in Germany, Wuppertal Suspension Railway. It's been designed and created in 1901, so it's been there for a long time. Transports 25 million passengers yearly. This one is in Japan. This one started in 1988, and it's said to have 25,000 passengers a day. Why these designs are problematic for us? Why do we need to create something other than these? They do not have active suspension system. As you can see, most of these implement these type of train-like suspensions. They just basically suspend themselves and hang themselves, and then they just ride along the track. There's no ascension, descension in the track. It just starts to gradually, levels a little bit. They're very bulky. We're trying to have a smaller, compact, more modernized design. What kind of designs are more relevant to us that's been created or being working on developed right now? The few that I ran across was the J-Pod. This is very similar to our design. Transportation pods, smaller scale, a few people at a time. It's being developed in Secaucus, New Jersey. But as you can see from the video, what they have so far is very similar to us. It's just directly connected to the bogie, and there's no real active, no type of suspension being developed for this. And another one I came across that's kind of interesting, looks kind of cool, was the Swift, being developed in Boulder, Colorado. This one's more of a bigger scale. It's going to carry more people, but also no real designs for the suspension. They designed the bogies. There are a lot of designs you can see for the bogies, how it's going to work with the rail, but as far as connecting the cabin to the bogie, not many people have designed. This is one of the recent finds that we've had. This is the most relevant to ours. It's called the Mister. It stands for something I can't forget. And it's in the process of being developed. Very similar to ours. As you can see from here, it looks just like it. Maybe the cabin design is different, but the track, everything looks very similar to ours. But it uses 45-degree descension versus our 17 degrees. So it's a little more steep, and it uses a cogwheel design to get rid of the traction problem as it's going up and down. But it doesn't have an active suspension that we could have found about this. And as you can see on here, it's just connected with that pin joint. It's just connected directly. As it moves, it will just swivel back and forth. So there's nothing being developed about it. And on the website, there's actually tech@mist-er.com. There was a contact email. I tried to email them to see if they've had made any progress, because this has been going on since 2005. And I tried to find out if there's any progress on the suspension, how they managed to progress this, but they haven't replied to me. So I'm going to pass this off to Dale over here.
Okay, so we've all been in a shaky car, maybe haven't experienced something like this. It's from Ace Ventura, if you've seen the movie. But so here you're in a car, you're shaking all around. It's not very comfortable. If you're drinking some coffee, you're going to spill it all over yourself. If you're trying to write on some paper or something, you're just going to have a really messy situation. So it's really important to have vibration control in these pods. So in order to be able to have a pleasant ride, to be able to get work done, and there's a bunch of reasons that there would be vibrations. The track may have some irregularities in it, and the joints between the sections, there may be some unclean welding. There may be vibrations caused by wind or other factors that just shake the pod, and we want to make sure that it's as smooth of a ride as possible. So another part is we need to go at least 17 degrees of a tilt. And you can imagine going down a roller coaster, you don't want to be facing the ground as you're descending or completely reclined as you're going up. So we're going to have actuators that have the ability to control the tilt of the pod in order to keep it parallel to the ground as it's traveling along the side of the track. We also want to prevent any swaying that occurs from either accelerating or decelerating, or that just happens from either wind or other factors. So we're going to control that with our actuators. We also need to be sure that, since this is a suspended system, as it pulls up to a station, it needs to level to the platform. There's a bunch of reasons for that. For safety, you don't want to trip as you're entering the vehicle. For accessibility, for disabled people, we need to allow them to be able to board easily without assistance from some sort of operator or getting some bulky ramp out, or it needs to just be able to act, they need to be able to get on themselves and in a smooth transition. And it's just more convenient. You don't want to have to be, if you're rushing to and from, you don't want to have to worry about, okay, well, I might have to step up, step down. It just makes the whole experience much more smooth. So I'll pass it off.
So our main deliverable for this project here is going to be a working scale model. As you can see on the screen, we have a preliminary design. It's something we've actually finalized within the past couple of days. The cabin will be suspended from the bogie with 3 linear actuators. The mixture of rigid mounting and pin joints to control the angle and elevation of the cabin. And then we also have a telescoping suspension system that will be able to take this system that's constantly in tension and use a standard compression mode suspension system. Just close up on this slide here. It's kind of hard to tell with the way that the picture is put into the slideshow, but the top piece connecting to the bogie is a larger cross section than the one on the bottom, so there are 2 tubes going inside one another. The inside tube has a pin coming out the slot in the side of the top one, and there's a coil over here to absorb any vibration that the cabin is going to be experiencing. Our number one goal for this project is to manage our resources well. For power, we need to make sure we aren't taking too much power that we're generating with all of our solar power, because we're just going to take away from the name of the project saying that it's green and more energy efficient. We also need to make sure we manage our own power and we don't spend too much energy on parts of the project that may not be as valuable as other parts, and we need to make sure that our energy is evenly distributed. Money is also a large resource that we need to make sure we have taken care of. We don't want to make this a project that's so expensive and kind of unrealistic that we aren't going to be able to come up with the capital and the parts to make this project finalized. And we also need to look forward for future projects. We don't leave them with a design that's going to cost them a lot of money to continue upon. Also, our third resource is time. We don't want this to be a long production type part where if we need to make 2 or 3 of them, it's going to take us 6 months. We want to be able to have a design that is readily made within a few days. Also, we need to manage our own time. We all have classes that we're doing, but we need to be able to devote our time to this project in an efficient manner and be able to meet the deadlines that we have set. Another goal is an aesthetic and non-intrusive design. It's the 21st century. Everyone's seen the new iPhone that just came out and all the other products we have on the market, the Tesla Model S. Everything is sleek and it looks nice. You don't want to ride an old tractor to work. It's clunky, it's dirty, uncomfortable. It's not appealing. You wouldn't want to pay, $3, $5 to ride that to work or school. But if you see a Cessna, a nice jet, it looks classy, it's sleek, and you know it's going to be comfortable. That's something you wouldn't mind paying a fare for to ride to and from your destinations. And then also our most obvious goal is to meet all of our functional specifications that Dale pointed out. We want to be able to meet all of these, both function-wise and time-wise. We know some of our goals may be a little out there, and it may be hard to reach, and we also know some of them are going to be very easy. Along with those goals, they need to be done with certain deadlines, and I'm going to go into that more with our Gantt chart. It's kind of hard to see on the screen here, but the first few weeks we spent creating our team and making sure we had the right people in our team that were dedicated to the cause, people that were unsure. We made sure that we got them directed to the teams that they needed to be on, and the guys that wanted to be on our team, we made sure that they were able to stay on our team. We've spent the past 3 weeks now coming up with initial design ideas and finalizing our design, and we have completed that. Our deadline, you can see from the Gantt chart, was today, and we have all agreed upon our final design that we're going to move forward with.
All right, so I'm going to cover the challenges section. It can be broken down into 5 parts: functionality, power demands, interfacing to the bogie itself, which is going to be changing, scaling, since we are working on a quarter scale, it needs to work when it is full scale, and then finally manufacturing and fabrication. So for functionality and control, first things first, we need to achieve proper damping and isolation vibration. To do that, we're probably going to be using coilover shocks like what you can see over here on the model. We do need to find out what the suspended weight is going to be. It's going to be an approximation, but we need to be as accurate as possible. Since we are doing a quarter scale, it's kind of going to be an estimation, but we do need to be accurate so that way it translates to the full scale model. Availability and costs, we probably will end up going with coilover shocks as they are readily available, and you can find them with different damping constants and spring constants. So it's just a matter of us determining what the weight will be and the deflection that we need to be able to withstand. For the tilt function of the cabin, we need to be able to tilt it at a 17-degree angle. And to do that, we decided that linear actuators are the best bet, as you might have saw in the sketch that we showed you. Electric linear actuators will probably be our best bet because of the power demands, which I'll talk to you in a little bit about. But these will be able to control the cabin angle, but they only need to be able to work when we need them to work. So they need to basically be hidden or just not be there until we need them to work. So to do that, we need to isolate them from the suspension system itself. We don't want to put undue deflection on the coilovers because that'll just sacrifice the suspension and basically change the dynamics of how they operate. And the other part that's tied into the tilting would be the leveling to the platform. To be able to do this, we need to then engage these linear actuators to bring up the deflection of the springs to whatever predetermined height of the platform may be. Also, like I said before, these need not interfere with the suspension while it's going, so these need to be isolated above. And something major to consider, what Scott said about the goals, we need to manage our money as best we can. So finding the right linear actuators that can support the loads that we need and fit the sizing requirements that we need is a challenge that we need to address. So power requirements, we all know this is going to be a 100% solar powered system. So therefore, we need to choose the linear actuators in mind with power in mind. We think that electric will be the best because we don't have to add any hydraulic systems or compression systems using pneumatic or hydraulic actuators. This is just our best guess so far, but with solar power in mind, we have a limited amount of power, and so therefore choosing wisely with the actuators is something that we need to consider. Interfacing. Everything's kind of changing this year with the design. The bogie is probably going to be changing with the switching mechanism. The tracks may be experiencing modifications, so we need to be open with the way we design our suspension. It needs to be adaptable, so that way if there is a change, we're not stuck with, oh no, our suspension can only mount up this one way. For example, I was kind of approaching a cantilever type suspension, which may work, but it's definitely not the simplest way to go about it. Scott, the design that we all settled on or agreed upon, it's pretty simple and straightforward, and it can be easily adaptable to mount to the bogie in a smaller area rather than using a cantilever with rotating arms and things of that nature. So we just need to be concerned or keep an open mind to how we're going to attach it to the bogie, which we might not know how it's actually going to be built at this point. Scaling. You can see here this is a half-scale, fully operational car. Just because we're building a quarter scale doesn't mean that it only has to work in quarter scale. We need this to work and translate to full scale, fully operational. The parts that we research now, not only do we need to have them work for our scale, but they need to be available in the full scale model. So if we can find actuators and coilovers for this scale, we need to make sure that the upgraded, the full size 4x scale would be available, and it's not a complete redesign from going from where we are now to the full scale model. And finally, manufacturing and fabrication. We need to consider the cost and practicality of everything we design. We can come up with a design that is wild and crazy and it may work great, but if it's not easy to build or it's not reasonable, then it's probably not going to be the right option. We need to consider that this may be a mass production enterprise where we're going to be building hundreds of these things. So choosing how we fabricate these things, or choosing design in mind with fabrication and manufacturing is important, so that way it's something that can be designed readily and repeated over and over and over again.
So we've broken the team responsibilities up amongst ourselves. My name's Scott, and I'm the team lead. I'm also in charge of the critical path schedule. I will also be floating around with these guys, helping them wherever they need help. If someone's really loaded up, then I can step in and help them out. Tyler's going to be researching hardware, and he's also our team liaison. Because he is in charge of the quarter scale team in general, he'll be talking with all the teams, and he'll be able to readily offer information to us and from us on a daily basis. NJ is working on our budgeting and ordering parts and materials, especially with his experience in being a treasurer and working with the treasurer here. We definitely felt like he was a good fit for that position. Matt is going to be researching all the controls for maybe the actuators, for the leveling system, any sensors we need to detect elevation and tilt. He'll be in charge of that. And Dale's in charge of our meeting minutes. He's taking care of making sure all of our meetings and decisions are documented. So if we ever need to go back to a meeting from last week and see what we discussed and what we decided upon, we have a record of everything.
All right, so this in review went over this intro as to why we're doing suspension, literature review, functional specs, deliverables, challenges, and responsibilities. This concludes our presentation. Is there any questions?
So I have a question. How many degrees of freedom do you need for your suspension? So right, the cabin is like a rigid body from dynamics, 6 degrees of freedom, right? 3 rotations, 3 translations. So how many degrees of freedom basically is your suspension going to actively control, and how many will be sort of passively locked out, rigid?
So, and we got either 2 or 3 freedom.
Should be 3, I think.
It's 3.
So
3
it seems
degrees.
like you have the pitch, that's 1 degree of
Pitch.
freedom, right?
Vertical.
And then, okay, so that's 1 rotation, and then you have a translation vertical.
Yes.
And then what else? Are you going to control this side to side?
No.
Sort of roll then?
Yeah, we haven't addressed anything in terms of roll.
Okay.
Probably just bushing mounts and
Okay, so
things of that nature.
pitch, then Z, and what else?
So it's
The
those 2 degrees of freedom, the rotation and the translation vertically,
That's it?
is our main focus. Yeah, we looked into kind of side-to-side roll, and that's going to be if we are moving down the rail extremely fast and we go into a corner and it wants to make the cabin tilt outward, that's also something that should be addressed in the rail design, and having the rail being banked as well, instead of having that translational force of the bogie on the railway. So it was something that we need to dig further into. I'm not sure if we'll be able to get to it in this year's thing, but whether or not that is something that needs to be taken up in the rail design or in the suspension design.
Okay, keep it in mind. So you need to, if you only got 2 degrees of freedom, you want to constrain the other 4, and then actuate those 2 in a good way so you can get the control. So I want to make sure I understand your telescoping thing better later, not right now. But,
Okay.
so best designs are ones that can, in a sense, exactly constrain the degrees of freedom that you don't want to have flopping around, and without adding kind of extra stresses and extra kind of stuff in there. So we can talk some about that. Okay, any comments for this group? So Tyler, great opening slide, right? A little interactivity. Hey, what do you think about this? What's wrong with this picture? Right? Fosters a lot of really good. So you can be very creative with your slides here. It doesn't have to be everything all the same, kind of boring sort of AE method, but there's a good interactive kind of thing. So that was great.
Well, to just make a comment along these lines. Now, here I give you a little bit of an example of the different approaches. So at the top of one of these pages I saw, cabin leveling on platform, and there was a guy in the wheelchair. Now what if I had said, we will handle cabin leveling? Now you've made an assertion instead of a half a sentence. And it has not only more clarity, but it also has more punch. And I'll give you another example here I thought of. Scott, you said good resource management. What if you had said, we will manage energy, money, and time? See, it's active and it's direct. And so those are two examples of the difference between the old way of doing things and the assertion evidence method. Dale, I thought it was great, that little video. I noticed a couple others, short 10-second videos, 20-second videos while you're talking about something else. I think they really deliver the message nicely, and you can incorporate those in your presentations. And you can zoom in, and we could do some discussion if anybody wants some help on how to use PowerPoint to animate your slides and things. I'd be happy to help you with that, and maybe others can too. So those are a couple of my thoughts. Oh, and somebody a little earlier said you couldn't get a hold of the Mr. guy. I have contact information for him. I've been in touch. Oh, yeah, I can get you in touch with him.
Okay, very good. Thanks, John.